Hi scientists, today we'll be talking about mechanical advantage. For a warm-up today we have a free body diagram sort, then we'll get into some notes, and then we'll head back to forces based on our lesson yesterday and do a quick lab. For our warm-up, you're going to be given a pack of cards. Please find the 4 category cards. They're the thinner ones that just have words on them. And then sort the free body diagram cards into the 4 categories. My big hint for you is to think about balanced and unbalanced forces, right? When we have a free body diagram and we have arrows that are the same magnitude, the same length, what does that mean? And then when we have a free body diagram, when we have arrows representing forces that are different lengths, different magnitudes, what does that mean? Go ahead and take 5 minutes, work on your warm-up, and then come on back. All right, take a minute to take out your notes template. This is the same one that we were working with last time. The notes right above this were about free body diagrams, and now we're in the mechanical advantage box. I want to remind you about 2 important vocab words for today. First is force. We've been talking about forces. It's just a push or a pull on an object. And then we have work. You might or might not have talked about this when you talked about simple machines. I just wanted to remind you, work is a force applied over a distance. So I would do work to push a heavy box across my living room. I would be applying a force to the box, and the distance would be across my living room. When we're talking about simple machines, you are exerting a force on the machine or doing work with the machine, and the machine is exerting a force to do its job. So maybe I'm doing work by swinging a hammer, and then the hammer is doing work by hammering a nail into the wall, right? So I'm exerting a force on the hammer exerts a force on the nail. Mechanical advantage is the ratio of these 2 forces. So the output force, the hammer on the nail, and the input force, me on the hammer. So the same amount of work always needs to get done, but if I want to use less of a force than to do that work, then I want a high mechanical advantage, and I want my output force to be higher in what's doing that work. So if in the work that's getting done, I am putting in a lot of force, draw a nice big F in, but then the force from the simple machine is smaller, then I'm putting in most of the force to get that work done. That's a pretty small mechanical advantage, and that is just not what we're looking for. What I want is a big force by the simple machine, right? A big output force. And I'm just putting in a small amount of force in. And then I have a big mechanical advantage. The numerator is much bigger than the denominator in this fraction, and that's what we are looking for here. Okay, so as a reminder, force applied over a distance is work. And now we want to relate this to our simple machines. So the longer the distance that a simple machine acts, the greater the mechanical advantage. If work is force times distance, right, for the same amount of work, if I increase my distance, then the force that I'm putting in can be lowered. So let's think about a box that I'm trying to lift up onto a shelf. I'm going to put in a pretty decent amount of force to lift this box up on that shelf, right? I don't have a really big distance to do that work over. But if instead I use an inclined plane, and I have my box here, and my shelf is the same height, now my distance is the length of the inclined plane, and I have to push that box up the inclined plane. It's going to take less force to push that box up because the distance is bigger. And so this work is still getting done, the box is still getting on the shelf, but the simple machine, the inclined plane, is helping me do it with less force. And I can even take that one step further. If I have a really long inclined plane, right, a really shallow angle, and I'm pushing my box up that inclined plane, it's going to be even easier. I'm going to have to use even less force because my distance has increased so much. So now it's your turn to think about it. What was the distance in your simple machine? Think back to our jigsaw. I've done the inclined plane, but maybe think about another one if that was yours. Chat with someone next to you, figure it out, and then come on back. So first up, we'll talk about a lever. Often we're talking about a structure that looks kind of like a seesaw, and I'll have a weighted object on one end, and then I'll push down, apply a force on the other end, and the result is that that object will move up. If I extend the length of my lever arm, that heavy object is still here, so my distance here is increased, I will need to apply a much smaller force to do the work of lifting that box. And there's all kinds of cool science about the ratio of the lever arms and where the fulcrum, right, this pivot point is placed. So if you're interested in that, I would YouTube it or Google it, definitely check it out. For a wedge, let's think about a wedge that might be on a sledgehammer used to split a piece of wood. So here's my piece of wood, and if I have a pretty fat wedge that's working down into the wood, right, being slammed down into the wood to split that piece of wood, versus if I have a really long wedge being pushed down into the wood, this distance is going to mean that I need to apply less of a force to do the work to split that piece of wood. So this one is the better one with the longer distance. With a screw, we think about the length coming in the thread. So the thread is like the spiral that goes all the way around the screw. And the longer that thread is, maybe the closer together they are, the less of a force you will need to apply. Pulleys are pretty complex. Lots of times we'll have a pulley system. They're like little wheels that we run a rope through. And then on one end is a heavy object, and then on the other end we are applying a force. The goal would be, of course, to lift this object here. And again, I encourage you, if you're interested in pulleys, definitely check it out. There's all kinds of different ways you can set them up, the numbers you use, where you place them. But we want to think about the distance of basically the rope running through the pulley wheel as being what we want to increase, and that will decrease the force we need to use in order to lift that object. For a wheel, you can think about the circumference of a wheel. So if I have a smaller circumference wheel, I will need to apply more of a force. And if I have a larger circumference wheel, I will need to apply less of a force to do the work of pushing an object. And this is obviously for the similar sized object, whatever is on our cart or whatever we're thinking of. And then inclined plane, we're thinking about the length of the ramp. We talked about that in our very first example. Next up, I'm going to have you watch a short video about mechanical advantage. This is Bill Nye, who's going to walk you through 2 different examples. You can just watch through 2 minutes and 30 seconds. This doesn't need to take too long, but pause the video, check that out, and then come on back when you're done. Now we're going to switch gears. We're going to go back to our ideas of forces from last class, so setting aside the mechanical advantage for a little bit. Think about a small ball. Maybe it's a marble or a ping pong ball or even a tennis ball. How many ways could you exert a force on that ball to make it move? Maybe you could drop it or kick it or push it across a table. You could roll it into a wall that made it stop. You could roll it along a really bumpy surface and see the force of friction in action. You could tie a string around it and pull it. You could put it on a skateboard and push the skateboard. There's all kinds of different ways you can make that ball move. Do you think the distance and the speed of the ball's motion would be the same for all of these forces? If I push it across a table versus blow a fan on it and have it move from the fan, do you think it would go as far? Do you think it would go as fast? What about the acceleration of the ball? Would it speed up or slow down at the same rate for all of these forces? Today we're not going to explore with a ball. We're actually going to give you a Matchbox car to build an experiment around. So in groups of 2 or 3, you're going to think about an experiment you could do to explore the effect of forces on the motion of a mousetrap car. So perhaps you're going to want to change something about the force, and you're probably going to measure something about the speed, the distance, or the acceleration. I recommend using the Vernier app that we've been using rather than just like a stopwatch and a meter stick. You'll be a lot more accurate in your data. I fully expect that you'll be able to finish up the Motion from Different Forces lab by the end of class, but you're probably going to need some time at home to finish up the analysis question. So those will be your homework for tonight. And then in addition, we've been working on our early architecture projects. So for next class, please complete notes to answer 2 of the questions in the guidelines. You might want to do the ones about mechanical advantage since we just talked about that today, but you can pick any 2 you want. Ms. Rosen made an awesome graphic organizer to go with this project, so you can ask me, Ms. Cook, or her, Ms. Rosen, for access to that if you don't already have it. And notes and bullet points are fine. Don't worry about full sentences. We'll get to that when we make your final product. All right, have fun with this lab and good luck.